Today we're going to take a look at one of my favorite topics, and that is finding the volume of solids. So when you find the volume of solids, you typically do the base times the height. So for instance, the right cylinder, for the circular one, you have the base times the height, and so with the base times the height, we have pi r squared times that height. So this is the circular one, and then if you consider the rectangle base, we have length times width times that height. But what if we don't have a proper right cylinder? For instance, let's look at this object over here. Kind of looks like a loaf of bread. So if you look at this, with the loaf of bread, for instance, you can slice it up, and then you can just find the volume of each one of those slices. So for instance, we could find the volume of each one of these slices over here. And as you can imagine, that will give you an approximation. So what we have, for instance, we're going to take one of these cylinders, or one of these slabs, and we're going to find the volume of that. And just as the volume of the right cylinder before was the area of the base times the height, we have the area of the base times that height, or times that width in our case. So that's the volume of one slab. But we're going to now find the volume of multiple slabs and add them together. So this should remind you of Riemann sums. So the total volume then can be approximated by the summation of these n slabs of the area of the base times that height. So the volume of each one of those slabs. And again, just like Riemann sums, the way to get a better approximation is by increasing the number of slabs to infinity. So here we're going to increase that number of cylinders, those slabs, to infinity. We're taking that summation of those volumes. So as you've learned, mathematicians, we are lazy, so we don't want to have to write this every single time. So we have this fancy way of writing it, which is now called the integral. So we have the integral from a to b, where a and b represent the bounds between which that solid lies. And then you have your a of x, which is your area of that cross-section. So in this case, that loaf of bread cross-section, or if you think back to that right circular cylinder, the cross-section was the circle. Or if you think back to the rectangular one, you had the rectangle. So it's that area, and then again, times that height. Let's take a look at an example. A solid has a base that is bounded by the curve x squared plus y squared equals 49 and the y-axis. So for here, we have a curve, the x squared plus y squared equals 49 is a semicircle with a radius of 7. And then it goes on and says the cross sections through the solid perpendicular to the x-axis are semicircles with the diameter of the semicircle in the xy plane. So for instance, that diameter of that semicircle is going to go from the top all the way to the bottom. So that right there is an example of a diameter. So if I was going to take a 3D look at this, we would get something like this. Notice the base is a semicircle and the cross sections are also semicircles. So you can imagine it's a quarter of a sphere. Now my goal is to find the volume of this quarter of the sphere. And you might be smart and say, well, I know the volume of the sphere and I can just take a quarter of it. Well, that's great and dandy, but how do they even get that initially? So let's look at it from this example here. So the first thing to do is to look at the area of the cross section. So we've already decided that the area of the cross section is a semicircle. And so because of that, we have the area being 1/2 pi r squared. Well, we now need to decide what is r in terms of x. And how do I know to put it in terms of x and not y? Well, if I look at this, the radius is dependent upon where I am along the x-axis. And that gives me the idea that I need to write that r in terms of x. So we're going to write the r in terms of x. So if I look at the radius here, for instance, well, the way to find this is, notice it is the height of this function. And the height of this function we know to be y. So solving for y over here, I have y is equal to the square root of 49 minus x squared. Since r is the height, r equals that y, we have r equals the square root of 49 minus x squared. So going back to that original area, we have the area is going to be 1/2 pi times that r squared. So now that we have the area of the cross section, I need to figure out the bounds of the x. So I'm coming up here. Notice I'm starting at x equals 0. But because my radius of this semicircle here is 7, I'm going all the way until 7. So I have the bounds for my x to be 0 and 7. Now with my bounds and with my area, I'm able to find the volume. So volume, using the integral, we have the integral from 0 to 7 of my area equation, so that's pi over 2, times square root of 49 squared is going to be 49 minus x squared dx. And then I would integrate that and get my answer. We're now going to take a look at another example. So here we have a solid has a base that is bounded by y equals x, y equals negative x, y equals 4, and y equals 1. So here we have y equals negative x, y equals x, y equals 4, and y equals 1. And we're given that the cross sections through the solid are perpendicular to the y-axis are squares. So here I would have a square that's perpendicular to the y-axis. So similar to the previous example, we need to determine what the area of the square is. So now that we know the cross-section is a square, well, we know the area of the square is just the side squared, so that s squared. What is s now in terms of x or y, and which one should we use? Well, unlike the other one, here, now the square is dependent on where it is along the y-axis. And so because of that, it must be written in terms of y. Or if you want to think about it a different way, because it is perpendicular to the y-axis, that cross-section is perpendicular to the y-axis, it has to be written in terms of y. So what is s now in terms of y? To determine what s is in terms of y, we're going to go look at the curves. So for instance, this curve is y equals negative x, and this curve over here is y equals positive x. And so now, what is this distance right here? To determine that distance, we're going to take always the right minus the left value. But we want it in terms of y. So again, thinking in terms of y, we have x is equal to y. And over here we have x is equal to negative y. And so because of that, we're going to have the right minus the left. So y minus the negative y is going to give me 2y. And that is the distance. And so s is going to be equal to 2y. Now with the s in terms of y, I can go back to my original area equation and write that in terms of that y. So I have the area is equal to, this is going to be 2y, that quantity squared. The next thing to determine is the bounds. So what bounds are we interested in for y? So coming back over here, we know the bottom y is at y equals 1, and then this top y is y equals 4. So we have the bounds to be 1 to 4 from our y. And I'm now ready to solve for the volume. The volume is going to be, again, that integral. It's going to be the integral from 1 to 4. All of that area equation, because remember what we're doing is we're summing up an infinite number of cross sections. So we have the integral from 1 to 4, all of this area, so it's going to be 2y, that quantity squared, dy. So to generalize, we have the volume of a solid can be found by summing up an infinite number of cross-section areas. And we learned this is just the integral. So if the area is dependent on x, so in other words, that cross-section is perpendicular to the x-axis, we have the volume is equal to the integral of that area dependent on x dx. And if instead that area depends on y, so dependent on where it is along the y-axis, so that means it's the cross-section is perpendicular to the y-axis, we have that the volume is going to be the integral of the area dependent on that y dy.